Okay, so today I'm going to talk to you a little bit about the transition between diffusion to flow. And so far we have been thinking in a very small scale at which molecules or particles that are fluorescently labeled inside of the cell or perhaps on the membrane are moving and are diffusing very quickly due to the nature of the motion inside of the cells. But now if we want to scale out a little bit, and one of the things that I really like about studying things in biology is how some of the phenomena that we observe are sometimes scale free. So the things that I like to think about and to observe in nature in general. Okay. Oh, okay. Does it work? Yes. Are how different elements can come together in a collective and start acting in a very particular or special way, and how some properties emerge when one and two get together and create something different that is not expected. And so sometimes today what I'm going to talk to you about is how we can use this kind of techniques that we have been talking about to be extended to other scales, and also how we can take advantage of the fact that we can tune our sampling in time and in space to modulate how quickly and which parts or which dynamics we want to pick up specifically. So what I am interested in is in when the molecules and the cells start to display phenomena like this one, which is here. Go. So what I study are more in this scale of things in which we have cells. These are neutrophils that are migrating under agarose, and they're activated by a chemotactic agent that makes them move very, very quickly. And this is a little bit the analogy of what Lionel was telling us earlier about single particle tracking. If you have a single pedestrian in the street, you can see and identify that person and keep the track of them. But what happens when we have more than one and we get very crowded spaces? That is what I want to show you. Okay. So when it gets really crowded, then sometimes we can have this kind of movement in which each cell here is labeled, the nucleus is in red, and the actin cytoskeleton is in green. And the movement of the cells is not all of them are going in the same direction, but in general, your eyes are able to pick up the flow of these cells and how they're going in a particular direction. In the biological case that we are interested in is the human umbilical endothelial cells, which display this particular characteristic in which when most part of the cell lines that we are familiar with are sufficiently confluent, what they will start doing is they will run out of space, and so they will just extrude themselves out of the monolayer or stop proliferating and die. But these cells have the capacity to start forming these streams of cells. And what we have been looking into is how can these cells know where to go? They don't have a specific leader. No one is telling them where to go. However, what we have found out, and particularly Arnold Heyer has found out, is that these cells are able to couple their movement with the cells in front of them and ignore a little bit more the cells that are around them. So this is the biological motivation at the bigger scale. So somewhere in between the bigger scale of tissues and in the micro scale of proteins diffusing inside of the cell, we're gonna be able to move in this space of image correlation spectroscopy. And to talk and to explain a little bit better what image correlation spectroscopy is, I'm gonna go back a little bit to what we saw this morning. And I know that today you will have heard about many, many different techniques. And so just to remember and to explain again, what are the difference between what we're going to talk about and what we have seen this morning. So fluorescence correlation spectroscopy, as has been explained by Michelle, is a fluctuation of fluorescence as a function of time. So if you imagine this volume, which is defined by the way that the light interacts with the optics of the microscope, you have a region in the center of this volume in which the particles are being excited the most, and so therefore their intensity is bigger or is greater at the center of this profile, and it's less so outside. And something important to keep in mind is that this observation volume that we call is not really a closed door kind of environment. It is a gradient, or it is a space that is a function, right? That is a point spread function. It is a function at which the intensity decays as a function of space, both in x, y, and in z. And if we imagine that we're looking at this volume from the top, and we have these particles that are diffusing in and out of this diffusion volume, well, they might be occupying different positions as a function of time, and as they come in and out, they contribute to the intensity fluctuations as a function of time. If we are using a laser scanning microscope, what we get is really just intensity as a function of time. And it's this very similar to what Michelle was explaining in the morning of reporting, one person reporting how many molecules they're seeing, right? It's just a record of 1, 0, 0, 0, 1, 0, etc. So we have this intensity fluctuation as a function of time. And what we define as a fluctuation is what is the fluorescence at time t, any time at this in this trend, minus the average of fluctuations. And this allows us to scale or consider that the intensity of one sample with respect to the other will be different, but what we care about is the fluctuations, or this delta F. Now, the autocorrelation function, as we saw this morning, it can be literally seen as what are the fluctuations at time t, this tau, and normalized over the intensity, the average intensity squared of the fluctuations over that period of time. And the autocorrelation function provides us with information on the number of molecules, as we saw the G0, or the amplitude of the autocorrelation function. 0 time delay gives us the number by the inverse, and also the decay, the rate at which this decay gives us the dynamics and how quickly this diffusion is happening. We can also, as it was also mentioned this morning, do two-color correlation, and then we can see what is the diffusion of the molecule A, the molecule B, the heterodimer, for example. However, now what we're going to do is use STICS, which is a correlation on the fluorescence, but in terms of space, so in x, y, and time. Now, this allows us to extract the flow velocity. And this is the main advantage that this has in terms of new information that we can extract from the sample. The correlation function looks a little bit more messy, but it's exactly the same. It pretty much just means that we have now x and y and time instead of only time. And we have, of course, the delays in x and delays in y. Very briefly, and this is very nicely explained in this annual reviews paper by Enrico and Michelle. The image is shifted with respect to itself, a given amount of pixels to the right and to the bottom, and this creates a correlation image, which looks something like this, and can be seen in a 3D dimension as this peak. And this is what the core of STICS is. So I'm gonna delve into this a little bit more detail later. But just to start where we picked up from this morning, the autocorrelation function and the cross-correlation function is a concept that very in mind. And to understand that in this case, in the fluorescence correlation, we have dots as a function of time. And the operation of this, intuitively for me, is more clear to see it like this. It is literally displacing the image with respect to itself and multiplying each of the coordinates of this trend times the one that is behind it, and dividing it or normalizing by the intensity. If you think of it this way, it is a subtraction followed by a multiplication and then a division. And this operation is very time consuming if you do it manually, if you do it directly like this. But the advantage is that we can go into Fourier space, and in Fourier space, the autocorrelation operation is literally just a multiplication. So that allows us to go much faster in the calculation of this correlation function. Now, if we try to extract diffusion coefficients from fluctuations, what we have seen so far is that the faster the molecule goes, the quicker the correlation function decays. And this is explained graphically in this example, in which we have a number of particles that are fluctuating in a volume, and usually this number of particles is very low, in the order of 1 to 6 to 10 maximum. And we have talked a little bit about why is that. So this is exactly the same signal. It's just extended on one side so that you can see slow diffusion with respect to fast diffusion. And we correlate, or we compare how does this look like this or like this. So the difference in the blue trend between this point and this point is much less than what it is in this point and this point, because so much more has happened in one of the trends. So hopefully this can give you an intuitive understanding of why and how we can extract the diffusion from the autocorrelation function in FCS. And hopefully by now you also know that this looks in general a little bit like this. When you have fast dynamics, they decay very quickly. When you have slow dynamics, they decay slowly. And so the similarity of the signal with itself is preserved for a longer period of time. That's the way to understand it. And we have also seen that the number of molecules is inversely proportional to the number, to the amplitude of the correlation of tau zero. So the more diluted your sample is, the higher the amplitude will be, and the more concentrated it is, the opposite. Now, how about oligomerization? And Lionel has explained to us the number on brightness method. And there was a question about, well, if we have a molecule that is diffusing freely in 3D, and all of a sudden now it's a dimer, it forms a dimer. Now it's very similar to thinking of a dance, and you can dance on your own, but then when you dance with someone else, you take a little bit more space, right? So it was mentioned this earlier about the hydrodynamic radius. And the hydrodynamic radius is related to the molecular weight and to the specific viscosity of the medium in which you're in, and the Avogadro number. And the diffusion coefficient depends on this hydrodynamic radius with the Bolt constant and the temperature and the viscosity of the medium. Now, if we substitute one with the other, you can see that now the molecular weight, if this doubles, only the square root or cubic root of that, the inverse of the cubic root of that number will scale with it. And we can see in this relationship how diffusion coefficient depends on the molecular weight and how for example, if we have a fluorescent protein like M. ceruleum, we have a small molecular weight and a high diffusion coefficient. But if we, for example, have a protein of interest that we want to label with it, diffusion coefficient has decreased. And if we have, for example, a dimer, now we have an even more decreased amount. But the problem is that, as you can see in this relationship, the more you are higher in hydrodynamic radius, the difference between them in, yep, this one's not working. So the difficulty lies in the fact that the more the higher the hydrodynamic radius is, the difference between these in terms of diffusion coefficient gets smaller and smaller. So it's harder and harder to identify the difference between monomers and dimers just based on the diffusion coefficient. So that's why the number on brightness approach works better for stating or estimating oligomerization states. Now, one of the most important lessons, I think, in spectroscopy, and I think anyone you meet and talks to you about it will not stop repeating it over and over again, is that if you acquire the data in the wrong regime or in a regime that doesn't capture the dynamics you're interested, it doesn't matter how you analyze it, you're not going to be able to capture it. So you really need to match the spatiotemporal regimes of what you're interested. And for that, it depends, as Lionel said, some techniques have some limitations. And after a given spatiotemporal dynamic regime, then you have to jump to another technique. So in this case, for example, for rotational diffusion, for blinking or diffusion of a small molecule in solution, FCS is the scanning FCS and raster image correlation spectroscopy are the techniques in which the laser scanning goes sufficiently fast to be able to capture how quickly those molecules or those dynamics are happening. What we're going to talk about today is more on the slow version or on the slow regime of this. So temporal image correlation spectroscopy and its extensions are more on the range of what vesicle transport looks like. And this is something we're perhaps more familiar in the kind of imaging that we have seen in optical microscopy. And what happens when you don't match the spatiotemporal regimes appropriately? So this is raster image correlation spectroscopy of a molecule or of simulations of molecules that are moving at 100 microns per second, 10 microns per second, 1 and 0.1. You notice that the autocorrelation function of RIX has the elongated shape that is due to the way that the laser scans the sample from left to right. But the molecule is the same correlation that you would have in other techniques because it's already too slow. So the point is you want to oversample in time, and you most part of the time are already oversampling in space. Now, to oversample, first let me just finish with the time. This is a diagram that was shown by Michelle earlier this morning. Is the smaller the molecule and the fastest the effect will be here. So if you sample at a given rate over here, you're going to be sampling way too fast, and you're not going to see the decay happen so quickly. But you want to be, you rather be in that regime than being over here. It's literally like coming to check if the bus has passed every 2 years. You will miss it every time, or you will not have a good information of how quickly are things happening in that regime. So you need to make sure that you match it. But I would say more than match it, you want to oversample it. So most part of the times our images, what they look like is just, it looks like noise or it looks like nothing is happening. If it looks like nothing is happening, that's a good sign, because then you have a lot of statistics on the things that are moving sufficiently slow with respect to how quickly you are acquiring. So I think this is one of the most important things to consider if you want to do any spectroscopy in your lab, to do the appropriate sampling both in space and in time. Now, if we want to go from from time-dependent signals to images, we need to consider that many of the microscopes are either laser scanning microscopes or camera-based microscopes. And in the case of RICS, we have the scanning point that is moved across the image, as we said before, from left to right and from bottom to top. And eventually it comes back here. So what we end up with, and this was also a question that came up earlier, is that as a function of x of the line, you have a microsecond delay time between one pixel and the next, and that's the dwell time. And then between one line and the next, you have a millisecond delay time. So effectively, you have space because this pixel is located at a different point, and you also have time correlations or time information because now you have information at what happened at time t, and this is time plus the delay of the line plus the 2 delay of the pixels in this case. So what we need to keep in mind is that by acquiring images in a camera, we're acquiring all of these pixels at the same time, almost at the same time, or virtually at the same time. So we do not have any more of that temporal information within one single image. So we're already going slower. As has been mentioned before also, the technical advances have allowed us now that we have some instruments that are allowed to capture images much, much faster than it was possible in the past. And so we're closing the gap between what laser scanning microscopes were able to do, which were very, very fast, and what images in cameras can be acquired. And I must say, the laser scanning is very fast, again, in the pixel dwell time and the line dwell time, but between frames, it was much slower because of all the time that took to scan the whole image and come back. Whereas the image camera-based goes much faster in frame to frame. So you need to consider what kind of equipment you have, what kind of dynamics you want to analyze, and based on that, what kind of technique I am able to use to determine, for instance, diffusion. Now that all of this, and hopefully all of this has been a recap of this morning, and most of this is clear, and if not, please feel free to interrupt. But now we're going to start going to the next step, which are the ICS, STICS, and STICS. And for me, the most intuitive way to go is instead of starting by ICS, I rather start by TICS, so temporal image correlation spectroscopy. Now we have, let's say, 5 images or 5 frames that we have acquired sequentially, one after the other. And what we're going to do is to compare, similar as we did in FCS, how does the signal look like itself as a function of time delay? In other words, we're going to compare frame 1, for instance, with frame 1. And it's going to look exactly like itself. So the similarity will be maximum at that delay time. And we will do that for all of the other frames. And this similarity between frames, which is identical, will be averaged later. But now we're going to start considering frame 1 with frame 2 with frame 3, 4 with 5. And this is literally exactly the same as shifting the delays of the time lapse, right? The time series is exactly the same idea, but there's now with images. Now we have stacks of images. And we keep doing that for increasing delays, and this is the tau, until we go out of taus, let's say. And this is why in FCS, you have many, many, many points. Sometimes at the beginning, or back in the days, it was almost millions of points. Because if you have only 5 points, 5 frames in this case, the first autocorrelation function, which is the yellow one, will be generated by 5 points, but you lose points every time. So you run out of information and your statistics gets weaker and weaker, and as you phase out of your observation or your comparison space, right? So for illustration, what it looks like is after we have these values of correlation or similarity between the frames, we average them and we get the correlation at time 0, at time 2, at time 3, etc. And this decays exactly the same as the correlation functions that we had. Again, our image-to-image, frame-to-frame correlation is generally much slower. So we don't really catch this part. Most part of the times, we only catch this part, which looks like an exponential decay. So again, you want to make sure that you're as fast as possible. And in principle, from the temporal image correlation spectroscopy, you can extract the diffusion coefficient in the same way that you do it with FCS. It's just that in this case, you have a decay of that region of interest. Now, you have as many pixels in X and as many pixels in Y squared to obtain information from. Now, you don't only have information from one point, you have much more data points in your sample. So one could argue that the determination of this correlation decay might be more accurate if your estimates and if your sample is appropriate. So this is temporal image correlation spectroscopy. Now, one step behind or before is image correlation spectroscopy, and this is the shifting strategy. So now instead of just shifting in terms of time, like we did with FCS and FCS and STICS, sorry, now we're gonna consider that we have, for example, 2 channels. One is green, and let's say we start with an autocorrelation. So we have 2 times the same image, and we shift it in space as more and more, either to the side and to the bottom and to the bottom right. Now, if the image is exactly the same, so I have 2 copies of the same image, there's no point on going to the left and to the top, right? Because it's exactly the same as if I had gone to the right and to the bottom. It's symmetrical. Now, if I have 2 channels, for example, one in red and one in green, we can do the exact same thing, and we generate this correlation function, which looks like this, in which the pixel in the center corresponds to no space delay. And as it moves to the right, we have different values, and it decays laterally, and as it moves downwards, it decays as well. Now, this is a similar concept than in RIGS, but you need to keep in mind that all of these pixels were acquired at the same time, whereas in RIGS, there's a very big time jump from one line to the other. Right? Whereas here, every pixel has been acquired at the same time, so the distance in time between pixels is the same. Now, this gives us special information, and as Michelle mentioned, if you have a point emitter, in other words, something that is fluorescent and that is so tiny that you can consider it to be much smaller than your pixel size, you can then use this approach to characterize the point spread function. So to characterize the point spread function, which is something you would need to do if you wanted to spectroscopy anyways, you have mostly 2 options. One, you can have EGFP in solution diffusing freely. So it's a diffusion coefficient that you already know, and you do raster image correlation spectroscopy to determine what is the Gaussian function, the width of the point spread function that would give you the known diffusion coefficient. Or in the opposite, you have beads that are fixed in your sample, and you know that they're not moving at all, and you just take images of them, and you try to make sure that you don't have clusters of beads, you have them sparse. And if you have just dots here and there, this image correlation spectroscopy would give you the characteristic size of the thing. That is the spatial information that it gives you. What is the characteristic size of the things that I'm looking at? So if you have an homogeneous distribution of all of the beads are exactly the same, you would get a point spread function estimation using ICS. Now, the jump to spatiotemporal image correlation spectroscopy is literally just to combine these 2. First, we have acquisition frame by frame of an image, and we're gonna take only a small region of interest of this image, usually goes to the 2 to the n, so 8 by 8 or 16 by 16. And we do that over not the whole image stack, because most part of the times what we're observing will have changed by the time that the video is over. So we take a small time of interest, which usually is between 5-10 frames maximum, perhaps more if you're able to oversample more in time. And we take these 5 frames and we first do the autocorrelation of each of them with themselves, like I showed you with STICS. But in this case, we're doing the image correlation spectroscopy, not just how much does the image looks like itself. We have a correlation function, as image correlation function for each of these comparisons, which it shows how as the delay in X and the delay in Y, or the shifts in X and Y, change the values of this correlation function. And we can average all of these 5 and get what we call the tau 0, so 0 delay. And we do the same with increasing distances in time between frames, and we keep getting less and less frames, less and less correlation functions to be averaged to generate the global correlation function. But we do get some information, we can get some information from this correlation functions, and that is what STICS really leverages or takes advantage of. If you like it better, this is exactly the same as doing the other representation of comparing one frame with the other. It's the same idea, but now we're doing ICS at each time point. So how do we get flow from this? The idea or the trick is that, let's say, in this case, we have 2 stacks, A and B. So this is just to show you that this is exactly the same image. What I'm doing is just to put very explicit that this is a particular case of the 2 correlation function. You can do it with 2 different channels, so actin and myosin, or whichever other molecule you want. In this case, we're looking at a human umbilical cell, and this is labeled with myosin. So these little dots are bundles of myosin that are moving as a function of time. Oops. Okay, it moved very quickly, but still. The point is that we're going to compare how the green and purple regions look like each other as a function of time. And when we do that, we can visualize it in two dimensions or in 3 dimensions, on which we're going to take the information of the pixels that are inside of this radius, and to those pixels only, excluding the ones outside, we're going to fit a Gaussian function. Very importantly, we're also going to omit the pixel in the center. And why is that? Why would I not use the one that gives me the most highest value in the correlation function? The reason is because you have an idea? No? The reason is because if you capture an image, there's always a contribution of your fluorescent labeled molecules, but also of the noise of the detector, of the noise of anything. And the noise correlates with itself only at no time delay. So this peak or this value of the correlation function will always be greater than your Gaussian function that you try to maximize its fit to the rest of the surface. So that's why we ignore that point. And we also ignore the points outside because sometimes you can have some periodicity, and this can show up in your correlation function. So here it is showing me that there is perhaps a characteristic distance over this axis or this direction that is more similar to, the image is more similar to itself over this other direction. So you want to avoid taking into consideration those because most of the times you're fitting a symmetrical Gaussian. And as time delay goes by, the peak of this Gaussian or of this correlation function will displace itself, in this case, from left to right. And so we know that to match the images the most at the maximum delay, we need to move them one with respect to each other to the left. So for it to look like itself the most, I have to go to the left. That means that the molecule moves to the right. So by doing this, we extract directly this flow estimation. And what I have been doing is to generate a graphical user interface called the ICS Explorer that allows you to do this iteratively, but for very many different small regions of interest. And what is an advantage of this software is that it allows you to go to any region that you're interested in and inspect what the information that was given to the algorithm was, what did it look like, to play through it, and then to see what is the result in terms of magnitude, rotation, angle, etc. And this is just a map of the magnitude. So you can see which regions were considered valid and what is the magnitude of the diffusion or of the flow in that region. Here's another example of the ICS Explorer being applied, in this case, photosums, and I will talk to you a little bit more about this on Thursday, in which these photosums are actin-rich structures that move laterally inside of the cells. And so you can see that in this region, to which we can zoom in, we have this vector that was generated by this region of interest. Now, this brings me to something very important. for me to generate this vector using the information in this image, it means that I am calculating the average displacement of the whole region of interest. So one big assumption is that I'm using that information that I showed you of the coordinates of the Gaussian peak to calculate the flow just exactly like this. So we have it displaced over to the top. And we can fit the displacement in x to the time delay with a linear function. And this has the intrinsic assumption that things are moving without acceleration. The displacement as a function of time is the same, and therefore we have an homogeneous or coherent movement of, at least in that region of interest, at least within that time, that is linear. And then we're going to take advantage of the fact that we can move very slowly in terms, instead of looking at frame 1 to 5, now we're going to look at 2 to 6, 3 to 5, etc. And so by doing this, we have linear fittings at every time step, but we eventually have this feeling of the flow. So that is one big assumption of STICS, and you need to take it into consideration. So the size of your region of interest has to be such that everything that is moving in that region of interest is moving at the same rate during the whole 5 frames that you're choosing, for example, and they're all moving in the same direction or more or less the same direction. And that's what you're going to capture with STICS. So that's why you have to tune that region of interest size very well. And the power of it is that if you have small things and big things moving fast and moving slow, you can use the size of the region of interest and of the time of interest to capture and distinguish both of them and to disentangle fast and slow dynamics in your problem of interest. So with the displacements in x and y, we can trace the coordinates of the center of the Gaussian, and we get the vector that goes with it. Now, one thing that was mentioned earlier today, and you have probably heard already a lot of acronyms this morning, but I want to take a moment to just explain the similarities and differences between STICS and other techniques that have been mentioned before. In few words, STICS would be to only consider the center pixel of this and how the Gaussian function decays as a function of time delay. So as you saw in the animations, it moves, but it also goes down, right? So if you stay at the center point, regardless of where it moved, that would be STICS, because you're not considering any time, any space displacement. However, you can measure that decay, which is due to diffusion, in another way. You can also measure how the width of the Gaussian function moves. And that is essentially the same thing as IMC. So image mean square displacement is a technique developed by Carmine Di Rienzo and Enrico and Francesco Cardarelli, in which if we have, for instance, here, simulation of flow only, you would have the peak only displaced. If you only had diffusion, then it would just go down. If you have the two of them, then it would look like there was two different things at the same time. So IMSD takes advantage of this and literally does STICS. It's pretty much just doing STICS exactly, and then measuring what is the sigma or the width of this Gaussian function that is being fitted as a function of time. And in this particular figure, they show that it's equivalent to look at the maximum of the Gaussian function if you just have flow. So how it decays. So this would be the width of the Gaussian function, so IMSD, and this would be the height of the Gaussian function, so STICS, in other words. And they are equivalent. They're independent, but equivalent in two ways to measure the same thing. The advantage, or what is easier to understand and to conceptually visualize with IMSD, is that sometimes you have this picket fence model in which molecules inside of the cell, sometimes because of the cytoplasmatic and cytoskeleton structures, can be confined to a given length, characteristic length, and sometimes they can jump from one to the other, and sometimes they cannot. So by using IMSD, you can distinguish these different dynamics, in which if you have only diffusion, then your IMSD as a function of time will increase linearly, whereas if you have it caged in a given space, you will find the size of that space by looking at what point it plateaus and stays stable. If you have a jumping probability, then you will have a caging space, and then after which you have a linear diffusion outside of that, and you can distinguish active transport or trapping using IMSD. Now, single particle tracking was also mentioned before, and it's another way that you can get a movement of biological samples. The challenges, in my opinion, about using single particle tracking is that it relies on the step of localization, which requires you to have some kind of assumption of what your molecule looks like, at least in terms of a Gaussian function that you fit, and then you find the molecule. You say this is a molecule, and then you trace that pattern by doing the same thing over a similar image and finding the nearest neighbor. And you just match that it was the closest, but it has some problems in terms of the tracking because it only works well at low density. As Lionel said, if you have very high density, it's very likely that one molecule or one particle would be confused with another one. If two particles go one on top of the other, whoops, oh, that was not the right touch. Sorry. All right. Yeah, if one molecule goes, oh, I use this only. If one particle goes on top of the other, then you have overlaps, and then you don't know who was coming from where and who's the next one. And if there are sometimes no connections that are clear enough in the closest neighborhood, you might find some connections very far away that seem to be big jumps, and so you can have artifactual increases of this. Another technique that is also mentioned and similar to STICS is particle image velocimetry. And particle image velocimetry has been in the field of engineering for years. This is 1940, and this fellow Ludwig Prandtl created this, pretty much it's like a fish tank in which he added water in here, and he had this manivelle to create a flow. So inside of this chamber, there's a horizontal wood piece that is not continuous. So all the water that he makes move towards the front comes down in the bottom and then recirculates on the top. And by doing that, he creates a continuous flow that he knows about. And by adding iron and gold particles to the water and using a camera here in 1940, he was able to acquire images of how the particles would go around something in the shape of a wind, for example, and explain how the turbulence or the flows of water go around different objects. So he could put cylinders or whichever objects he would want to. And what PIV does is literally using some light source that has this like light sheet shape, and orthogonally you have a camera that is capturing this. This is literally like looking at dust when the sun comes in through a very thin vent in your window. And by taking pictures one after the other and comparing one with the next, you can calculate the flow vectors for this kind of movements. What this looks like is more or less something like this. And so your eyes can have an idea of how this is moving from one to the next. Now, the big difference between PIV and STICS, because it's essentially taking advantage of the same idea of image correlation, is that in particle image velocimetry, you have the correlation is done between each pair of images. So the TI is always 2. You only compare frame 1 with frame 2 with frame 3, and that's it. It is designed to detect the flow of macromolecular independent particles like beads in liquid. So it doesn't take into consideration that things might be interacting with each other, or that you might have some other diversion in the flow that are not due to some object that placed in there or something like that. It can provide flow velocity measurements, but in comparison, STICS can use correlations over a longer period of time. So again, the faster you sample, the more points you will have, and the better you will be able to do it. It can consider non-independent particles, so molecules that experience fission, diffusion, binding, fission being here used in a very broad sense. And it can extract local concentration because we have the amplitude of the correlation function. It can extract the diffusion coefficient if you only have diffusion, cross-correlation between two channels, and also account for the coexistence of this with flow. So with that, I want to thank you all for listening, and thank to the Instituto Profesor de Montevideo, to my colleagues at the McGill University, and also to the LFD lab, and very particularly to Enrico and to Lionel for having me here and for welcoming me to the LFD family. Thank you so much.